So far, I think you used more or less rectangle coordinate systems, Cartesian coordinate systems. You are very much familiar with those. But in addition to that, there are several other types of coordinate systems that we could consider for our analysis. One such coordinate representation is called polar coordinate representation. That is, we represent instead of x and y and z, of course, we represent it in a by using the vector distance r and angular displacement theta. That is, using r of this is the point, the particle location, and this is the position vector, and this is the direction theta. So using these two quantities, we could define the position of this particle. So that is called polar coordinate representation. So as you know, this rectangle representation of this coordinate system is x1 e1 plus x2 e2, and the point is the coordinates of this point is x1 and x2, and we define x1 r cos theta, r sin theta, and then we define unit basis vector in the direction of the radial direction. I call it n hat r, and the direction I take is radially outwards. So radially outwards, that means that is the direction of this vector r, exactly the direction of this vector r. So I want to make it a unit vector, therefore I divide the vector by the magnitude of the vectors r. So if I use what I get is the vector representation of this n hat r is cos theta e1 plus sin theta e2. And then I define another vector which is perpendicular to this n hat r. I call it n hat theta, that is the direction of increasing theta. And since this is a perpendicular vector and again a unit vector, then the first derivative of this is the definition of this vector. Therefore, n hat theta is minus sin theta e1 plus cos theta e2. And these kind of vectors, as I just mentioned, can be represented using matrices. So this is read as n hat r equals cos theta e1 sin theta plus sin theta e2. N hat theta equals minus sin theta e1 plus cos theta e2. So these manipulations you will learn in the next semester. And then when it comes to three-dimensional motion analysis, representation of these vectors in the form of a matrix is a must. So there is no other way of mathematically handle this. Just highlighting this, but since we are doing only two-dimensional analysis, we can manage without this stuff. Now, when you consider a particle moving in a polar coordinate system, r and theta system, then nr hat is, we just looked at cos theta e1 plus sin theta e2, and if you get the first derivative, we get n hat r over dt, like this. This is the first derivative of this, and that will be if you get the theta dot out, so this one in fact is n hat theta. That is the definition that we just looked at earlier in the previous slide. Therefore, this becomes n hat theta. Therefore, the first derivative of this unit vector dn hat r over dt is theta dot n hat theta. Similarly, if you get the derivative of n hat theta, so this one, you will get this one. And if you get theta dot out, then what is left over here is exactly this one. Therefore, d n hat theta over dt equals minus theta dot into n hat r. So this is n hat r. So this is also important for us in our discussion. So this is dn at r over dt, and this is dn at theta over dt. So this one is theta dot n hat theta, and this one is minus theta dot n hat r. So that is the relationship between the two directions. And the position vector r, if I define in n hat theta and n hat r frame, so this is, but I'm interested now is not defining things in the E1 and E2 frame, that is the fixed frame, but I'm trying to describe the motion of this particle particle P in the form of with respect to or with reference to this new coordinate system that I just defined, n hat r and n hat theta. And of course, this is a coordinate system attached to this particle. Therefore, when the particle moves, this coordinate system also will be moving. So if this is moving in a straight line at a constant speed, of course, that will be inertial reference frame. But most of the cases, using polar coordinates and all, we are trying to work out problems, particles moving in a complex curves. Therefore, this this point P is going in a curved path most of the time. Accordingly, this new coordinate reference frame, that is n hat r and n hat theta, is a moving frame, and most of the cases it is a non-inertial reference frame. But anyway, with this position vector P, we can define in this n theta hat and n hat theta and n hat r frame, there is r into the unit vector n hat r. And the velocity is the first derivative of this. Then the velocity becomes r dot n hat r plus r dn hat r over dt. And we just found that dn hat r over dt is theta dot into n hat theta. Therefore, the velocity is r dot, that is the velocity component in the n hat r direction. And this r theta dot is the velocity component in n hat theta direction. So the two directions, these are the two components of velocities. So this is the radial velocity of the particle, because this is the radial direction. So this is the with respect to the fixed coordinate frame or the universal reference frame in this case. And this is the angular motion of the particle, that is rate of change of radial vector. This is the rate of change of radial vector that makes the angular motion possible. So if you apply this one to a situation where r is constant, so if r is constant, it's a circular path, then r dot becomes 0 if r is constant. Therefore, you will get only one part, r theta dot, in the direction of n hat theta. Accordingly, v becomes r omega, if theta dot is omega, r omega, and this n hat theta direction is the perpendicular to the radial direction. That means it is the tangential direction in the case of a circle. So this is the tangential speed, v equals r omega. So it is exactly the same that we looked at earlier using vectors, but now we obtain it using polar coordinate representation. Now this is the velocity in general for situations where r is not a constant. So r dot n hat r plus r theta dot n hat theta. To find the acceleration, of course, you can get the time derivative of this one. So if you get the first derivative, what you would get is this one. So you have 2 terms in this one and 3 terms in this one. So you'll have to differentiate these 2 separately and these 3 separately, one at each time. So what you would get is this. And then you can replace this d n hat r over dt and d n hat theta over dt from the equations that we just obtained. And if you substitute those into that equation, the equation becomes this. And if you take this n hat r terms together and n hat theta terms together, then your final answer will be this. Now, this is an interesting relationship. There are 4 terms, 2 directions, and 2 terms in each direction. This is the rate of change of radial velocity, which is independent of the angular motion. And this is the centripetal acceleration, radial inverse acceleration. You can see this n hat r direction we have defined radially outwards, if you can recall. So this n hat r we have defined radially outwards. So anything minus means radial inwards. And then we have angle acceleration r theta double dot, that is in the direction in the direction of n hat theta. So so that is a normal direction to radial direction. And this one is 2 r dot theta dot, we call Coriolis acceleration. We call Coriolis acceleration. That in fact a very important part of this exercise. That is, if you can recall from my first lecture, that is, I showed you the observations with reference to rotating reference frames, and this Coriolis acceleration to r dot theta dot is in n hat theta direction. That means it is perpendicular to the radial direction. And if I go back to that small video clip I showed you on that day, so I'm talking about this video. So you can see this one is rotated at a constant angular velocity. So by using a motor or something. So r theta double dot is 0 in this case. There is no acceleration in the tangential direction. And now you can see it is rotating at a almost constant angular velocity. And we are watching it from a Earth fixed coordinate frame. So there are no, which is a inertial reference frame, and the ball travels along a straight line. Now you can see the camera is in the rotating frame, so it is not an inertial reference frame. And what happens to the ball is, as you saw at the last class, the ball tends to we see it as it is moving towards left to the curved path. So that means there is force component applied on this, which pushes this ball down. There's a force which pushes this one down this way. That is how earlier it was a straight line, now it is curved like this. In order to do that, in order to get that, there has to be a force, and that force appears only when the frame is in rotation. Frame is moving. Now frame rotates. So that in fact we call the Coriolis effect. So the ball has a mass, and the Coriolis acceleration component with the mass exerts a force. So that is called the Coriolis force. And the Coriolis acceleration, we just found it for the particular situation, of course, is in the tangential direction, perpendicular to the radial direction. And if the frame is rotated at a constant angular velocity, this r theta double dot term is 0. Therefore, this is the only acceleration in the theta direction. And that theta direction force, theta direction acceleration in combination with the mass of the object create a force, and that force pushes that ball down. So that is how it happens. And now in this case, we have, when you represent acceleration like this, then we have considered this Coriolis effect in our equation. Therefore, we can apply Newton's laws without any trouble because the necessary modification has been done. So, so that is about the effect of Coriolis acceleration. And one final thing that I just want to tell you about the Coriolis acceleration is, now we have Coriolis acceleration is a product of 2 r dot theta dot, and we have two directional vectors. So the r dot is measured radially outwards, and theta dot is measured in the counterclockwise direction. Therefore, Coriolis acceleration depends on the direction of this as well as this. Now, for example, in a particular situation, if the acceleration is radially inwards and rotation is counterclockwise, then Coriolis component becomes negative because r dot is in the negative direction. Or else, even r is in the right direction, but you rotate the system in a clockwise direction instead of counterclockwise, then this is theta dot and this is r dot. Again, Coriolis component is negative because one of the vectors is in the opposite direction. But of course, since this is a product, then if the Coriolis component is radially inwards and the rotation is clockwise, this is r dot and this is theta dot, then both vectors have changed their directions. Therefore, the product will not change its direction. Minus into minus is plus. Therefore, you get the plus quantity. So when you are calculating the magnitude or the Coriolis component, then understanding this direction or figuring out the direction of these two different components is very much important. Otherwise, you might get the wrong sign in front of it. So in all these analyses, we have considered rotation is counterclockwise and radial direction is radially outwards. Now, if you apply this relationship for a special situation where r is constant, again a circular path, then r dot is 0. So velocity is v into n hat theta. So if it is a circular path, of course, this n hat theta becomes a tangential direction because n hat r is a radial direction towards the center of the circle. So if the circle defined from the center, so this becomes tangential and this becomes radial direction of the circle. And acceleration, of course, r double dot becomes 0 because r is constant. And then the r dot also will become 0. Therefore, the Coriolis component also becomes 0. Therefore, acceleration is r minus r theta dot squared in the radial direction and r theta double dot in the theta direction. And again, you can see reason why there is a minus sign here because we have defined our n hat r radially outwards. And we know that this acceleration component in a circle is always radially inwards. Therefore, we'll get this minus sign over here. And this is basically what I just wanted to tell you about the kinematics along complex curves. And with that background, I hope we can look at a couple of problems and see how this concept is applied in different situations. Let's look at a small example to see how we could use the
polar coordinate systems to analyze a problem. So in this particular example, there is a slotted arm OA. Slotted arm OA forces the small pin P, this pin P, move in the fixed spiral guide. So this is the fixed spiral guide defined by R equals K theta. So the equation of this guide is given by R equals K theta. R is distance from this turning point of OA to the position of P. So theta is increasing in counterclockwise direction, measured with reference to the horizontal direction. Arm OA starts from rest at theta equals pi by 4. When theta equals pi by 4, the velocity or theta dot becomes 0. Angular velocity of OA becomes 0. And then it will be accelerated at a constant counterclockwise angular acceleration, theta double dot equals to alpha. So alpha is the angular acceleration, which is again in the counterclockwise direction. And we are asked to find the magnitude of the acceleration of the pin P when theta equals 3 pi by 4. So that is the problem. And first of all, we don't need all these nice geometric information to work out this problem. So we represent this using a very simplified diagram, keeping only the essential information for our analysis. Now, first of all, we can define our polar coordinate system. Now, this arm OA rotates about this point O. So we'll make measurements from the turning point or point of rotation O. And let me take, this is the direction, this is the radial direction. And I can define my N at R direction radially outwards like this. And the perpendicular direction towards the counterclockwise direction is N hat theta. So those are the two mutually perpendicular unit vectors that we use in polar coordinates. So we can get rid of this geometric information, leaving or keeping only the essential information for our analysis. And what we are looking at is the acceleration. And a while ago, we obtained an equation for acceleration, that is A equals radial component of the acceleration and the theta directional component of the acceleration. And this radial component has two parts, r double dot minus r theta dot squared. And theta directional component also has two components, r theta double dot plus the Coriolis acceleration, which is 2r dot theta dot. So remember, r dot theta dot term, or the Coriolis acceleration, to be positive, this has to be moving in the counterclockwise direction, and r has to be measured radially outwards. Now, if I say A equals radial component plus the theta directional component, so AR becomes AR and A theta are this component and this component, as seen here. And in the data, it is given that R equals K theta and theta double dot, or the angular acceleration, is alpha. And we know that they start moving from theta equals pi by 4, and it moves up to theta equals 3 pi by 4. At that point, we want to find the acceleration. So we know that theta dot equals 0 when theta equals 5 by 4. And what we are looking for is the acceleration when theta equals 3 pi by 4. Now, in order to find this acceleration, we want to find r double dot, r theta dot, r theta double dot, r dot and theta dot. So all these quantities we need to find when theta equals 3 pi by 4. So once these components are found, we can substitute to this a r and a theta and find the acceleration. Now it is given that r equals k theta, then r dot is k theta dot, get the first time derivative, both sides, and r double dot equals k theta double dot. We know that theta double dot is alpha, therefore r double dot is k alpha. So at theta equals 3 pi by 4, r becomes k 3 pi by 4, and r double dot also we know it is k alpha. But to find r dot, we need to know theta dot. So the next mission has to be to find theta dot. Now, to find theta dot, we could look at the problem from the fundamentals, where theta double dot is the time derivative of theta dot, that is d theta dot over dt. And now I don't know about any information about time, but the information about the variation of theta is given. Therefore, I would like to separate this equation or manipulate this relationship such that I bring in d theta into this one. And if I do so, then d theta over dt is theta dot. Accordingly, I can get rid of this dt term and represent this theta double dot in the form of d theta dot over d theta multiplied by theta dot. So with slight rearrangement of this, I would get alpha d theta equals theta dot d theta dot. So this alpha comes here because we know that theta double dot is alpha. And now we can integrate this equation, this relationship. Theta goes from pi by 4 to 3 pi by 4, and theta dot at theta equals 5 by 4 is 0. And what we are looking for is theta dot when theta equals 3 pi by 4. So I can integrate this one within those limits. Theta goes from 5 by 4 to 3 pi by 4, and theta dot goes from 0 to theta dot. And if you if you integrate this and substitute limits, you will get theta dot squared equals alpha pi. And accordingly, theta dot is square root of alpha pi. And once you find it, then you can find r dot also, because r dot equals k theta dot we found earlier. Accordingly, r dot will be k square root of alpha pi. And earlier we found that r equals k 3 pi by 4 and r double dot equals k alpha. So now we have obtained all parametric requirements to calculate AR. So you can substitute R double dot from this one, R from here, and theta dot from this one, or theta dot squared from this one. And with the substitution of those parameters, you would get AR equals K alpha into 1 minus 3 pi squared over 4. Just a substitution, you can simplify it and find. And a theta, on the other hand, again, we can find, because all these things we know. So substitute the corresponding values. Then a theta will become 11 over 4 k alpha pi. Now we can further simplify these parameters, substituting phi equals 3.14 and simplifying this. you will get AR equals minus 6.4 K alpha, A theta equals 8.64 K alpha. And the magnitude of acceleration, we know that it has to be the square root of squared of theta component plus square of R component. And those two components we found. So if you substitute these quantities over here and get the square root, you will find the magnitude of acceleration. That will be 10.76 K alpha. 10.76 K alpha.